Hey guys, in this video we're going to be talking a little bit more about our ionic bonding. So we're going to be at the end of this video, hopefully be able to describe bonding that goes on within ionic compounds, and then know what atoms are going to form in order to produce our ionic compounds, and then looking at our metals and nonmetals, know what ions are going to be formed using our periodic table when we're talking about our main group elements. Okay. So when we think about an ionic bond, remember this is going to be a bond between two ions. So we have a cation plus an anion, and that forms our ionic bond. Okay. And generally with our ionic compounds, our atoms within there form those ions in order to achieve a noble gas configuration. So most atoms, our main group atoms, or main group element atoms, will form ions in order to be isoelectronic to the noble gases, as in form a noble gas configuration. Okay, so in the case of our metals are all the way to the left. They're going to be closest as far as most closely related electronically to the noble gas before it. So they're going to lose electrons in order to become isoelectronic with a noble gas. As a note, our transition metals have d electrons, so they're not going to follow this trend. So those d electrons, these are valence electrons in the case of a transition metal, unlike any of our other main group elements. So they don't try and achieve a noble gas configuration. Okay, but our nonmetals, since they're more to the right of our periodic table, they're just a few electrons away from their noble gas to the right of them, so they're going to gain electrons. Okay, when we think about our formation of an ionic compound, it is a redox reaction of elements. Okay, so what I mean by this is if we take our elemental forms and we put those metal and nonmetal atoms together, a redox reaction is going to occur, and the metal is going to transfer a valence electron or valence electrons to our nonmetal. So when a nonmetal and metal atom are in contact with sufficient energy, the metal will transfer its valence electrons to the nonmetal. So if we think about sodium plus chlorine going to sodium chloride, we can look at this as a redox reaction where we have sodium going to a sodium ion plus an electron, and then our chlorine adding an electron going to a chloride ion, and then the sodium ion plus the chlorine ion forming our sodium chloride. So we have our oxidation, half of our reaction, and our reduction, half of our reaction. So like I said, with our main group elements, we're trying to achieve a noble gas electron configuration. Let's look a little bit more at that. So our S and P block elements, and like I said, these are our main group elements. They form ions to achieve a noble gas configuration. So let's look at a couple of different things. So look at a metal example. So if we have lithium, lithium is 1s2, 2s1. Helium is going to be the noble gas that is closest to it electronically. So we just need to remove this electron. And what we get is one less electron, which gives us a plus charge, and an electron configuration of 1s2. Take something like nitrogen. Nitrogen is 1s2, 2s2, 2p3. Electronically, this is closest to it. So if we add 3 electrons, then we get 1s2, 2s2, 2p6, and a 3 minus charge, which would give us that isoelectronic 2 neon electron configuration. We could do that for each one of our atoms that we form ions, or we could just use our periodic table. So instead of going through and seeing, okay, what does my electron configuration need to look like in order to get a noble gas electron configuration, our periodic table already tells us this information by looking at what group number it is and then what group number our noble gas is in. So all of our noble gases are in group number 18. So it has 8 valence electrons, and we need to remove or gain electrons in order to get to 18. So with group 1, here we have 1 valence electron. So we're going to remove 1 electron, giving us a plus 1 in order to go to the noble gas right before it. Group 2, we have 2 valence electrons, so we will remove 2 electrons, which gives us that plus 2, and again, going to that noble gas electron configuration right before it. Our transition metals are going to have all sorts of crazy things going on in there, as will our lanthanides and actinides, so we're going to kind of just ignore those. With our group 13, we have 3 valence electrons, so we can remove 3 electrons in order to get to the electron configuration right before it, or the noble gas electron configuration before it, such as for boron will produce helium, or aluminum will produce neon. Generally, boron doesn't do this too much. It's more of a covalent species. Doesn't really form our ionic species all that much. And then we get to group 14. And this has to gain or remove 4 electrons in order to achieve that noble gas configuration. So this is not common either. So 14 will almost always covalent compounds, not our ionic compounds. So if it does, it will gain 4 electrons. And if we think about our ionization energy and our electron affinity, both of those are going to be so much energy that this really is not very energetically favorable, so not a very common species. Then we get to 15. Here we are 3 valence electrons away, 1, 2, 3, from our noble gas. So we just add 3 electrons, which gives us a 3 minus charge. 16, we add 2 electrons to get a 2 minus charge. And then 17, we add 1 electron, which is definitely the most energetically favorable, which is why these are halogens or salt formers, or salt forming, I guess, because all of them form a variety of different salts because it is very easy, very energetically favorable, right? It only has to gain 1 electron, and gaining that 1 electron is, when we consider electron affinity, that's actually going to be a release of energy. It is more energetically favorable for it to gain that 1 electron. So we will form all sorts of halogens, salts. So let's real quick just look at our transition metals. As I said, at some point, our most common ion for a transition metal is a +2 ion, and let's look at why. So transition metal ions themselves, they have more than 3 electrons that need to be removed in order to achieve a noble gas electron configuration. And that's a lot of electrons. So 3 or more is a lot. Some of them have to lose 10 electrons or gain 10 electrons in order to achieve a noble gas configuration, and that's just not very energetically favorable. So when we're thinking about our transition metals, we have to consider that our s electrons in this case are now valence electrons, not core electrons. So d electrons are valence electrons. So it is very hard to achieve that noble gas configuration. Instead, it's going to try and lose electrons that are highest energy to them. And almost always this means our s electrons. Our transition metals will form ions that remove high energy electrons. So usually the s electrons. And usually there are 2 s electrons. So the most common ion for a transition metal is a +2 ion. Okay? And let's look at an example real quick to see what I mean. So let's look at vanadium. If we look at vanadium, it has the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. And we talked about this in a module earlier on where when we remove electrons from a d block element or transition metal elements, we're going to remove our highest n value. So in this case, it's going to be 4. In this case, it's going to be 4, so we're going to be losing these 4s electrons. And that would give us a 1s2, 2s2, 2p6, 3s2, 3p6, 3d3. So it's easier to remove those 2 electrons that are in the highest energy state. Um, Vanadium will produce a +5 to try and get to a noble gas configuration, but this, just removing those 2 electrons and going to vanadium 2 plus, is very energetically favorable. Okay, that is everything I have on ionic bonding. I hope you guys understand a little bit better, and I will talk to you guys in the next video. Bye.